Let me take you further down into the rabbit hole. Task is actually a nice abstraction that we're using here. We're dealing with tasks. We have a scheduler that distributes those tasks over our available resources. MPI, the message passing interface, is in comparison more like assembler programming. Actually, older processors used to have fewer integrated circuits than we have cores on supercomputers these days. So the analogy is not that far off. Who has used MPI before of you, actually programmed with it? It's almost everybody. Then I can probably move through this fairly quickly, which is good. So the idea behind MPI is that we have multiple independent resources. In comparison to threads, which usually deal with a shared memory system, MPI, by basic assumption, we can work around that, but by basic assumption actually is a distributed memory system. So we have independent nodes that somehow should communicate with each other. The basic facility for that are communicators. Each MPI program has one global communicator, MPI ComWorld, that includes all the resources that are part of this job. How these resources are actually assigned to the MPI job depends on the system that you're using. So here and in Jülich we are using Slurm. So actually Slurm deals with setting up the resources and actually telling the MPI library on init which parts belong to this particular communicator. The communicator is used to send messages. That's why it's called the message passing interface. But to send messages, you need to know who is sending and where you are sending it to. So you need some kind of address. The one used for MPI usually is a rank. The ranks are negotiated on MPI init. So when the MPI process starts, basically the resources figure out which node should be which rank. So here we have rank 0 and counting to n-1. All right. There are different kinds of communicators. The lowest level one is the point-to-point communication. When you do point-to-point communication, you have a sender. So in this case here, it's 1. And it sends a message to 0. That's my receiver. For a regular send command, I have to give the sender and the receiver their default values, and they have to match. So if I have a send, I have to have the corresponding receive. Now with this, I can pretty much build everything. Since I can send messages to any arbitrary processor, I could, and messages here are usually data, I could just set everything up by hand. Luckily, I don't have to do that, because some of the typical operations that are done over multiple processors are done by collective communications with and then we can have something like this. We can, for example, have node 0 send a message to every other node. This could be, for example, a scatter. So I have data on rank 0, and I want to distribute the data to all my nodes. I could also, I don't have to care how this is usually implemented. And so, for example, this could also be a reduction. I want to sum up all whatever values I have on a single node. So I could implement a reduction like this. I could send all my values to rank 0 and there do the adding up. That's a valid way of doing a reduction. Does mean, though, that I have a serial part here that will limit, in the end, my maximum performance, because I can't be faster than adding up all those numbers on node 0. And I mean, this aren't necessarily just 5 numbers, but could be 2 million or 2 million times 10 to the whatever numbers that I want to add up. So the reduction could also, for example, be implemented like this, where I have multiple levels, like in a tree. That is often what the vendors do. There might even be more specific optimizations depending on the network that is available. So Cray, for example, implements their own reduction algorithms or general algorithms. And on the IBM Blue Gene P, they actually had a separate tree network. This tree network could do computation. For example, add up integers. So if you were doing a reduction with integers, it would actually do that on the tree network separately from the general communication torus that it had, and extremely efficient. So those are then vendor-specific implementations of MPI that you don't have to care about if you use this kind of functionality, rather than implementing everything with send and receive. By the way, you'll later learn that one of the versions of MPI for Pi for reduction does exactly this. I already mentioned that MPI for Pi, that MPI needs to, or has some setup routine. If you program this in C, you call MPI init. In Python, MPI init, when we use MPI for Pi, is actually called when we do the import MPI. At that point, it calls MPI init in the background and sets up the job. Here, I'm using the parallel magic from the IPython notebooks again. So once we have this, we actually have a communicator. MPI com world now is set, and I can do the typical thing and call rank and size to get my own rank and to know how many other processes are involved in my job to maybe optimize my scheduling. And here is our Hello World program complete. So this is now executed on all the IP engines that were started, in this case, with an MPI setup. So I'm doing the rank and the size. If I had 9 processors, this would be a nice Star Trek reference. And yeah, so I can do my Hello World in Python, even in a Jupyter notebook, quite easily. I do have point-to-point communication available. And here I'm mixing a little bit. So this is actually part of the IPy parallel API. I'm using a view. But I guess I didn't put that on here. But I can also now do the same thing with MPI calls. So I can, for example, distribute data, or actually I did the point-to-point communication before. I can then pull the results, for example, from a single node using then the IPy parallel, so to make this more interactive. MPI for Pi has 2 versions of most functions. One is uppercase, and one is lowercase. The uppercase version maps pretty directly to the C API. Actually, the API looks more like the C++ API, which has been dropped from the MPI standard. but it maps to the underlying C functions. It only works with NumPy arrays or other things that have a memory view because it directly accesses the memory. It's still more convenient than MPI calls are in C because, for example, it deduces the size and the type. And the overhead is really small. So those are the uppercase versions. There you have to give a send buffer and a receive buffer and have to watch out what you're actually doing. And then there are also the lowercase versions. So here is the uppercase version with the where I define a NumPy array. This is the send buffer. This is the receive buffer. Looks almost like the C program, right? Not that much difference. Except that, yep, I don't have to give the type nor the size of bytes that I need to pass. Very convenient. And the overhead really is minimal. There is the lowercase version, which in a way is really cool. I can feed it almost arbitrary Python types, almost because it still needs to be pickable. So it needs to be able to convert it into a stream because it needs to send it over the network. And it actually returns results. I really like the API here. I mean, this is nice. Usually, though, implemented as I'm collecting everything on one rank and don't do any fancy tree algorithms to optimize this. All right. So there are two notebooks. There's the Introduction to Dask and the Introduction to Python, to MPI, not Python. We don't do Introduction to Python.